Okay, so before we get to the optimization revision stuff, I want to go through the homework from yesterday. Did everyone try it? That's good. You're a bit more awake than my second year class. They're all half asleep. Okay, so let's start off with question 1. Okay, so 1.1. We had the function f of x equals ax squared. Okay, so very similar to what we did in class, so same procedure, but we've just got this a here. And we want to know what happens if we multiply this function by a. Okay, how does it change the result? So, same thing as always, we've got the definition for f star. We want to find that x prime, okay, in the definition. That x prime is the point that maximizes px minus f of x, okay, from last time. So we want to maximize px minus f of x. And the solution to this will be the x prime that we need to find f star. So this is going to be p minus 2ax. So x is p over 2a. And this is the x prime that we need. Okay, once we've got the x prime, we can substitute it into the definition, and that gives us our f star. So f star of p, remember that was px prime minus f of x prime. We know what x prime is now, so we can just substitute. So that's going to be p times p over 2a minus a times p over 2a squared. Okay, so the first term, we're going to get p squared over 2a minus the second term will be p squared over 4a. So we end up with a half minus a quarter, that's a quarter. So we end up with p squared over 4a. Okay, so very similar to what we had before, but notice that the a being multiplied on the x squared now goes down to the bottom here. So previously we just had 1/4 p squared. Now we've got an a over there. Okay, so that was the x squared example. Very similar to what we covered in class. For 1.2, we have f of x equals ln x. Okay. So again, same thing as before. We want to find x prime. What's x prime? X prime is the point that maximizes that difference. So it's going to be px minus ln x prime is equal to 0. From this, we can get our x prime solution. So this is going to be p minus 1 over x is equal to 0. So x is equal to 1 over p, and this is our x prime that we want. Okay, once we have the x prime, substitute it back into the definition, and that gives us our f star. So f star at p, that's going to be px prime minus f of x prime. So that's going to be p times 1 over p, because x prime is 1 over p. So that's just going to be 1 minus the natural log of 1 over p. You can leave it like that, or you can simplify a bit and write this as 1 plus log of p. Okay, again, you don't need to simplify, but if you want to do that, that's fine. Okay, who got this correct from the homework? Okay, good. Okay, nice. Yes. So I just used the log rules. So the log of x to the n is n log x. So here you can think of it as p to the minus 1. I just took the minus out. Yeah. Not necessary, but it saves a bit on the simplification. Okay. and then 1.3. Okay, f of x is equal to sine x. Okay, so this is going to be px minus sine x prime is equal to 0. From this, we get our x prime that we need. So this is going to be p minus cos x is equal to 0. So x is going to be cos inverse of p. And again, that is our x prime that we need. Okay, once we've got the x prime, we substitute and we get our f star. So f star of p, that's going to be px prime minus f of x prime. Okay, remember x prime, we just found that there. So that's going to be p cos inverse of p minus sine of cos inverse of p. Okay, now you could leave it like this, or you could simplify. You could write this as p cos inverse p minus the root of 1 minus p squared. Okay, who got this one? 1, 2, okay, 2. Okay, let's have a look at part 2. So that was showing that this process is its own inverse. So if you calculate f star, you get a function. If you calculate f star star, you get back to the original function. Okay, so the word for own inverse, fancy math speak, is an involution. Okay, you don't need to know that, but if a function is its own inverse, we call it an involution. Okay, so question 2. Okay, before we go through the solution, who attempted question 2? No one. Okay, it's a bit difficult, but it's not so bad. Okay, so all we want to do is start off with the function f of x, and we follow the same procedure. So we follow the procedure to get f star, and then we treat f star like we treated f, and we just do the process again. Once you do the process again, you end up back with f. Okay, so there's no like tricks to it, it's just doing the process twice. Okay, again, just a little bit of terminology. A function that is its own inverse is called an involution. Okay, so by this we mean, for example, f of x equals 1 over x. F of x just gets us back to x. It's its own inverse. You apply it once, you get f of x. You apply it again, you get back to x. That's what we want to do in this case. We start off with f. We calculate f star. We get f star. We calculate f star star. We get back to f. Okay, that's the goal. Okay, so for the proof, let's just recall what we know from the definition. So by definition, x prime is the point that maximizes px minus f of x. Okay, that was the definition of x prime. Okay, from what we did last time. Okay, so what does that mean for it to maximize this difference? It means if we take the derivative and substitute x prime, it's going to be 0. Right, that's the criteria for minimum and maximum. So px minus f of x prime is 0 at x prime. Okay, so we're just following exactly the same steps as we did for the previous 3 cases given f of x. It's just that in this case, we don't know what f is, but we can still do the process. There's nothing stopping us there. So this is p minus f prime of x is equal to 0. So f prime of x is p. But not just any x. This is the special x that we called x prime. So here, this is f prime. X prime there is p. Okay, and remember, we want to solve for x prime. Again, that's the process. We covered the process a few times now. So at this stage, we want to solve for x prime. So we would take the inverse on both sides and get x prime, which is a function of p. Look back at your previous examples. X prime, whatever it was a function of p. So x prime is a function of p. Since it's a function of p, let's give it a nice name. Let's call it g of p. Okay. This g of p is just shorthand for the inverse of the derivative. Okay. So this is just f prime inverse of p. Okay. But instead of writing all of that, I'm just going to call it g. Okay, so again, the proof is just following the procedure of finding f star. Okay, we've got x prime. Now what do we do with x prime? We substitute it in the definition and we get f star. So that's what we do. So f star of p is going to be px prime. Let's write it in order. Minus f of x prime. Okay, again, we don't know what f is, but we can still do the calculation. There's nothing stopping us there. So let's substitute. So f star of p is going to be p. X prime, I'll call that g. So let's put that there. Again, this x prime over here, I call that g of p. Okay. And that's it. We've got our f star. So we've done the process once. So what we've done is we've taken f of x and we have converted it to f star of p. We've done it once. That's the Legendre transform once. Now, what is the proof trying to show? If we do this again, we get back to f. So from here, we need to get back to f. Can we show that? So what we're going to do is take this function, f star, and treat it like the f we did in the beginning. So take f star and treat it like the f from the beginning. In other words, we do this procedure again, but not with f, but with f star. And then we get f star star. Okay, so how do we get f star star? Again, we just use the definition. So f star star at q, we need another variable. It's a different function. So this is going to be q q times x prime, but here we don't use x prime, let's use p prime, because we started with p, minus f star of p prime. So exactly the same thing as before. Now instead of x prime, we're using p prime, because f star was a function of p. And instead of p, we're now using a different variable, q. Okay, so this is f star star. If you block out the star over here and you replace q with p and p prime with x prime, it's exactly what we had at the beginning. Okay, now this p prime, yes? Oh, so the normal definition is f star of p is equal to p x prime minus f of x prime. That's the definition we had before. We want to find f star star. So f star star, we can't use p, that's already been used. We need a different variable. I'm going to use q. So P goes to Q. So wherever we have a P, we're using Q now. So P goes to Q. Here at the top, we have a function of x, so we used x prime. Now we're using a function of P, so I'm going to use P prime. You don't have to use P prime, it's just to keep the same naming scheme. Minus. Now we don't want to use F, we want to use F star. And this is a function of P prime. Okay, so we're just doing the process again with slight change to the variables because it's a new function. Again, what is P prime? P prime is that particular point where it maximizes that difference. Where P prime is the point that maximizes what does it maximize? It maximizes that distance that we had. So it maximizes QP minus F star of P. Okay. Previously, this would have been P x prime minus F of x prime, right? But now we're using the new variables. So what does this mean? This means we want to maximize this thing to find P prime. Once we have P prime, we can substitute it back. So we have to take the derivative, set it to 0, solve for P. So derivative d by dp set it to 0. This gives us P prime. So here, this will be valid at P prime. Okay. Exactly the same process as before. Before, this would have been d by dx, and we would have been solving for x prime. But this is the second time we're doing this process. So now it's d by dp at P prime. And we just carry on. We carry on with the method. So this is going to be q minus d by dp of f star p equals 0. Okay. Everyone with me? Okay, but what is this f star of p? We calculated that already. That is, if we go here, that's this. So we substitute that. So in the f star in the bit at the end, we now put that over there. So we're going to have q minus d by dp of f star. We calculated that in the beginning. That was p g of p minus f of g of p. And again, that was 0. Okay, so all I did here was take the derivative and then substitute f star from the previous step. Okay, let's do the derivative. So q minus, here we've got a product of two things, so we have to use the product rule. The derivative of the first thing is just 1, so we get g of p plus p g prime of p. Okay, everyone with me with that? Okay, p times g of p, so I get g of p plus p times g of p. I just use the product rule on this. So that came from the product rule with the first term. Now the second term over there, we've got f of g. So we have to use the chain rule. Good. So this is going to be minus f prime at g of p times g prime of p. Okay, so that came from there with the chain rule. Everyone still with me? Okay. Now I'm going to make a little bit of a simplification here. So that minus inside there, we can distribute that out. So this is going to be Q minus G of P minus P G prime of P plus, and then we have the F prime there. So the minus and the minus, that just makes a plus there. Okay. So what can we do now? Well, F prime G of P and G prime of P. What we want to do is try and simplify this a little bit, and then that will end up cancelling something there. Okay, so this is going to be Q minus G of P, okay, minus P G prime of P plus P G prime of P. Okay, so how did we get from here to here? Let's look back at our F prime over there. Yep. Okay. F prime of X prime. I'm going to rewrite this a bit. So here, this is equal to, remember, this X prime we call G of P. So F prime of G of P. Let's just write that, F prime G of P. That's P. That comes from this line, and it comes from this line there. Okay, so this X prime definition here, this G of P, if we substitute that back here, we get F prime G of P is P, which we needed over here, F prime there. Okay, so this F prime G of P over there, I replaced with P. Okay, does everyone see what I did with that? Okay. Now look here, we've got P G prime of P with the minus plus P G prime of P. They cancel. Okay, so finally we end up with Q is equal to G of P. But this isn't any particular P. This is P prime. Right, like we had with X prime. We did the derivative in terms of X, and then we called it X prime. Here, we do the derivative in terms of P, and then we call it P prime. So, G of P prime. Okay, very similar to what we did previously with the P equals F of X prime. Okay, same idea. Okay, so we've got our P prime, or in terms of the Q there. So what do we do? Think back, if this was X prime, we substitute it back. So we take this, we substitute it back. Okay, so remember what the definition is. F star star of Q. This Q acts like the P from the original definition. So it's going to be Q P prime minus F star of P prime. Right? Yeah. So we just substitute now. So Q is going to be G of P prime. So this, I'm just going to put there. Okay. Now remember the goal. Okay, don't get lost in all the algebra. The goal is to get this to F. On that side, we've got F star star. We want to show that F star star is F. So out of all of this here, we need to get this to F. Okay, please don't get lost in the algebra. Remember the goal of what we're trying to do. So from here, we want to get to just F by itself. Okay, so how can we do that? G of P prime, leave that alone there. f star of p prime. We know what this is. We calculated this. So we go back up here. F star there. F star of p, we're looking for f star of p prime. So if we put a prime on all of the p's, then we've got our answer there. So from here, I'm going to write f star of p prime. Okay, like we had f of x and then f of x prime. F star of p, we now have f star of p prime. I'm just changing the variable name. So that's going to be p prime g of p prime minus f of g of p prime. Okay, so I took that equation over there and I just renamed p to p prime. Is everyone with me? Yes, no? No. Who says no? All right. Okay. Are you with me or not? You're shaking your head. No. Okay. I'm taking that equation. Instead of p, I'm putting p prime. That's it. That's all I'm doing. Equation in the box, wherever I have a p, equation in red, I put p prime. That's it. Okay. Anyone still lost with that? Right. Okay, so we're here. F star of p prime. That's going to be the red equation that we had before. So this is going to be g of p prime minus, and then what we had in red. Okay, so that's going to be p prime g of p prime minus f of g of p prime. So that red equation with just renaming p to p prime, I'm substituting here. So I get this. Okay, in the front there, we've got g of p prime minus p prime g of p prime. They cancel. Minus and a minus, that makes a plus. Almost done. Okay, so we've got g of p prime. What is that going to be? Let's go back here. What's g of p prime? Q. So this is f of q. Let's look at the left. F star star of q. What's on the right? F of q. So what does that mean? It means that f star star is f. Okay. So it's just a bit more algebra because we don't know what the function is, but the process is exactly the same as if I gave you f of x equals x squared. We've done exactly the same thing. So here, if we go to the top here, if I gave you an f, then you would calculate x prime. That's the process. You calculate x prime. What do you do with x prime? You substitute it. That's the process. Once you substitute it, you get f star. Done. That's the first step. What do we do after that? We want to show that it's its own inverse. So we do it again. We treat f star like we treated f. So what do we want? We don't want x prime. We've done that. We want p prime. How do we get p prime? Take the derivative, solve for p. We took the derivative and we solve for p. And we call that p prime. What do we do with p prime? We substitute it. So f star star, we substitute p prime. And then the rest is just simplifying. we cancel, and we get f. That's it. You just do the process twice. Okay. Any questions on this? No questions. No one's going to be brave and say they don't understand. Okay, suit yourself. Okay, let's go through the optimization problems. Okay, again, next week, Tuesday, is a Friday timetable, so we're going to miss the tutorial. So your tutorials will be due Monday, no later than 12. Okay. So please make sure that you hand in your tutorials by 12 on Monday. And since we're missing the tutorial, we're going to be going through some extra problems today. Okay, so optimization revision. Okay, so I've got 3 questions here to go through. So number 1. Show that the line of shortest distance between two functions, between two non-intersecting functions is normal to both functions. Okay, so we've got two functions. We want to find the shortest distance between the two. So that's going to be a line between them. We want to show that the line is normal to both of them. For example, let's say we had a function like this and some function like that. The shortest distance is going to be where that little gap is. So that's this distance here. We want to show that it's normal to both the functions. So in other words, it's normal to both tangent lines. So we've got this tangent line in red, this tangent line in green. The shortest distance line is normal to both of them. Okay, everyone understand the problem? Yes. Sure. Okay, so that's the problem. Show that the line of shortest distance, so the straight line between the two non-intersecting functions. Okay, why do we take non-intersecting? Why does it have to be non-intersecting? Think about it for a bit. What happens if they're intersecting? Yeah? No. If they're intersecting, what can you tell me about the distance between them? Distance is 0. Yeah. Okay. So if they're intersecting, the shortest distance is automatically 0. That's not interesting. Okay. So they must be non-intersecting, and we want to show that the shortest distance line is normal to both. Okay. So let's start off with these two functions here. The first function, that point over there, let's call it x1, y1. This point on the second function, let's call it x2, y2. So let's say that's for f and that's for g. Okay, so we've got these two functions f and g. We claim that this point x1, y1 on f and x2, y2 on g, that gives the shortest distance. Okay, so let's find the distance and see if it's the shortest, or see what happens when it's the shortest. So the distance, or the distance squared, is going to be x1 minus x2 squared plus y1 minus y2 squared. Okay, let's make a little bit of substitution there. Y1 is on the graph f, so it's f of x1. Y2 is on the graph g, so it's g of x2. So this is going to be 2x1 minus x2 squared plus f of x1 minus g of x2 squared. Okay, everyone with me still? Okay, so now we're going to take the derivative. Here we've got a problem because we've got x1 and x2. Okay, we've got two variables. So we're going to take this in two steps. The first step is we're going to fix the first point and move the second point. Then in the next step, we're going to fix the second point and move the first point. Okay, so we want one variable. So we fix the one as a constraint, change the other, and then swap. So for one, we're going to fix x2, y2. So that's going to be our constraint. We're going to fix it in place and see what the shortest distance is. And then in the second case, we're going to fix x1, y1. If both of these are true, then it's the shortest distance. The shortest distance between the 2 points, it doesn't matter where we start, where we end. So the process of fixing the one, moving the other, or fixing the other, moving the first one, gives us the same thing. Everyone understand that? Okay. Okay, so let's call this f. We used f. Let's call it h. H of x1. That's going to be x1 minus x2 squared plus f of x1 minus g of x2 squared. Let's not do the derivative yet. So that's just h. We want to now find h prime. Okay, so h prime. Why? Because we want to minimize. Take the derivative, set to 0. Okay, so we're going to get 2 x1 minus x2 plus 2 f of x1 minus g of x2 f prime of x1 equals 0. Let's call this equation 1. Okay, so we end up with that. Okay, so we just took the derivative with respect to x1. Now we're going to do the same thing, but we're going to take the derivative with respect to x2. So this is the second part. So I'm not going to go through the whole process of the setup. I'll just write down the equation. So it's going to be 2 x1 minus x2 minus 1. Because we're taking the derivative with respect to x2, we need to use the chain rule. So the derivative of that will give us the minus 1 there. Plus 2 f of x1 minus g of x2 minus g prime of x2 equals 0. Okay, and that's our equation 2 from taking the derivative with respect to x2. Remember the minus signs over there because of the chain rule. Okay, we've got equation 1 and we've got equation 2. Now, these were non-intersecting. Okay, non-intersecting means that the points are different. So x1 and x2 are different, y1, y2 different points. So non-intersecting, what does that mean? It means x1 is different to x2. Okay. If they're different, it means the first terms over there, this x1 minus x2 and this x1 minus x2 on the 2 lines there, those are non-zero. If they're not the same, the difference is non-zero. So let's put that in red. This is non-zero. And this is non-zero. Okay. Everyone following with that? Okay. So what we can do is solve this simultaneously. So you can add the equations together, subtract them however you want to solve simultaneously, we're going to end up with f prime minus g prime. Okay, if you add them, subtract them, whatever you want there. F of x1 minus g of x2 over there, f of x1 minus g of x2 over there, they're also non-zero, right? Because the points are different, so they're different. So if that's non-zero, if we add them together, we're going to end up with f prime of x1 minus g prime of x2 must be 0, right? Because the first two bits there with x1 minus x2, they cancel. F of x1 minus g of x2, that's non-zero. We can get rid of that, which means f prime of x1 minus g prime of x2 must be 0. Everyone see what we did there? Yeah. Yes. So we're taking equation 1 and we're adding it to equation 2. This first one, 2x1 minus x2, is the same here, but with the minus sign. What happens when we add them? They cancel. 2f of x1 minus x2, 2f of x1 minus x2, it's non-zero. We can divide both sides. This side is 0, so that can just go away. It's non-zero, we can divide by that. What are we left with? We're left with these two. Okay. So this means f prime of x1 is equal to f prime of x2. So the gradients at the 1 point, sorry, that's the g. So let's call this m1 is equal to m2. So the gradient on the first curve is equal to the gradient on the second curve. So let's just draw the picture again. So it was like this and something like that. So this tangent line has some gradients. Let's just draw that a bit better. And this has some gradients. Okay. But the gradients are the same, which means the lines are parallel. Okay, they're parallel. Everyone okay with that? Gradients are the same, lines are parallel. Okay, so let's draw in the normal line. What can you tell me about the normal line and the tangent line? They're perpendicular, which is what we wanted to show. So, done. Therefore, the shortest distance line, sorry, can't spell shortest distance line is normal to both curves. Why? Because, well, the normal to the red and it's normal to the green is normal to both. Okay. Any questions about this one? Yes. Sorry? Yeah. Yeah, that's just taking the derivative with respect to x1. So the 2 comes down. Yeah, no, it's just the power rule. So the 2's over there is from the power rule with that squared and the squared. Okay. Any other questions? It's all good. Okay. So the next one, we're going to use this fact to then find what this distance actually is. So here we know that the shortest distance is normal. So it's a normal line between the two. We're going to use that fact to then find the distance. Okay, so number 2. Okay, determine the shortest distance between y equals x squared plus 2x and y equals 2x minus 1. Okay, so we've got these two functions. You can call the one f and g if you want, but we've got these two. We want to find the shortest distance between them. And we're going to use the fact that the shortest distance line is normal to both. Okay, that's going to help us quite a bit. So a quick sketch of this. We've got this thing over here for the parabola. Got a straight line over there. Okay, just a rough sketch so we can see what's going on. So we're going to have some points here, and we're going to have some point here, and they're going to have the shortest distance. There. Okay. We know that to be true. They're non-intersecting. You can check that for yourself. So between the red dot and the green dots, we know that that's going to be our shortest distance line. We also know that the shortest distance line is normal to both functions. If it's normal to both functions, it's normal to the tangents. So we can put in the tangent line. Okay. And what do we know? If they're normal to both tangent lines, their tangent lines must be parallel. Okay. Okay, we're making good progress. What's the gradient of the straight line? 2. So let's call this M2 is 2. What's the gradient for the parabola? We can't find that immediately. We need to find y prime. That's the gradient. So gradient, that's y prime. So y is equal to x squared plus 2x. We want the gradient, so we want y prime. That's 2x plus 2. Okay, so let's write here y prime 2x plus 2. Okay. So we've got that gradient there. This must be equal to what? 2. Good. We want the gradient of the red line to match the gradient of the white line. So if that gradient is 2x plus 2, and that gradient is 2, they must be equal. So here this is M1 equals M2 for the lines to be parallel. So we can solve for x. So dividing through by 2. Okay, so x must be 0. So on the parabola, these lines are parallel when x is 0. If x is 0, y must be? If x is 0, y is? 0. Good. Okay, so on the parabola, we have the points 0, 0. So that's half of the problem done. We've got the points on the parabola. To find the distance, we now need the points on the line. Okay, so we've got the points on the parabola. We need the points on the line. So this is part 1 done. Okay, so if x is 0, y is 0, and that gives us the points on the parabola. Let's put that in the red box for the red points. Okay, so how do we get the points on the line? Okay, well, we've got the equation of the line. That doesn't help us too much because it can be any points along there. We want that point. Okay, so what can we do? We've got the red tangent line. How can we go from the red tangent line to this line? We can use the normal. Use the normal there. So here we can calculate this normal line. Let's go back up. Okay. We've got the red line. Remember back when we did tangents and normals? We've got the tangent line. We can find the normal line. If we've got the normal line and this line, well, that's just the intersection of the two. Everyone with me? Okay. So next step, calculate the normal line. Let's put that in blue. Okay, it's like an in-between step. So once we're done with the parabola, we can use the normal line to find the points on the straight line. How do we do that? Well, the gradient of the normal line is perpendicular to the gradient of the tangent. The tangent line has gradient 2. So the normal line has gradient -1/2. Good. So we have y equals -1/2 x plus c. We don't know what c is. We need a point on the line. Well, that's good. We know a point on the line. This one. This point 0, 0. So that means c must be 0. Okay, so we've got the normal line. That's y equals -1/2 x. So we've got the blue normal line. We've got the white line G, if you want to call it that. Now we want to find the intersection point. That gives us the green point over there, this intersection here. So we take the two lines, we make them equal, we solve for x. Okay, so next step, screen there. Find intersection of two lines. Okay, so that's the normal line and the line that we're given. So -1/2 x is equal to the line that's given. That was 2x minus 1. Okay, so 1 equals 2x plus 1/2 x. So 1 equals 5 over 2x. Okay, so x equals 2 over 5. Once we've got x, we can find y. We can use either equation to find y. So y equals -1/5. Okay, just by using -1/2 x. So this is the point on G, on the straight line. Okay. And this was that green point. So we found the red point. This was the green point. So we can put that in a green box there. Okay, we've got the red point, we've got the green point. Now we just want to find the distance between the two. That's just the distance formula. Okay, x1 minus x2 plus y1 minus y2, both of them squared. And we know the points now, so we can just substitute. x1, that was 0. x2, that's 2/5. y1, that was 0. y2, that's -1/5. Squared. So we get root 4 over 25 plus 1 over 25. So that's going to be root 5 over 5. Okay, so that's the shortest distance between them. Once we've got the 2 points, it's just the distance formula to find the minimum distance. Okay, any questions on this procedure? Okay, so how do we find the point 1? The tangent lines must be parallel, so the gradient on the one is the gradient on the other. We can find the point there. How do we find the point on the second curve? The normal line is perpendicular to the tangent. So once we've got the tangent line, we can find the normal line. The intersection of the normal line and the other line, that gives us the point that we need. Okay, last question for today. Okay, we've got the following setup. Okay, so we've got a road at the bottom. We've got a building along the vertical. Okay, there's a window over there. We also have a wall over here. of height 2, and it's 1 meter away from the building. Okay, so this is our wall, this is our building. Okay, what we want to do is find the ladder of shortest distance or shortest height ladder that will go over the wall to the building. We want to get to the window over there. So this ladder we can put in red here is going to have a certain distance L. Okay, but ladders are expensive. We want the shortest one possible that will go over the wall to the building. Now you can think of this wall over there as like the pivot point. So you can have the ladder starting there and pivot over there. Or you can have it go like this. And that gives us a different distance. We can go closer to the wall here, but that moves us further up the building. We can go further away. Let's put that in blue. We can go further away here, and that will go lower on the building there. Here, there's some points in the middle that gives us the minimum distance. Okay, do we go closer to the wall or do we go further away? That's what we're trying to answer. Okay, so how do we do that? So let's introduce some variables. Okay, so same sort of situation here. We've got this triangle now. So forget the ladder. We want to find this hypotenuse, L. Let's have this distance be x. That's the distance away from the wall. And over there, that's the base of our ladder. We're going to call that x. Remember the distance to the building, that was 1. The height of this was 2. Let's call the height y. Okay, now we've introduced too many variables. We've got x and we've got y. We want one variable. But notice how the smaller triangle is similar to the larger triangle. They're similar triangles, which means the ratios are in proportion. So 2 over x is equal to y over x plus 1. Okay, that's just because they're similar triangles. So right away we can solve for y. So y is going to be 2x plus 1 over x. Okay, that is the constraint to the problem. Okay, right, because they must be similar triangles, so that's the constraint. So instead of two variables x and y, we now have one variable x. Okay, everything is now in terms of x. Let's find the distance. Let's find the distance squared, so L squared. That's going to be the square of the hypotenuse is the square of this side plus the square of that side. So square of the bottom, that's going to be x plus 1 squared. The square of the height, that's y squared. We've got that here. That's 4x plus 1 squared over x squared. Okay, so that's L squared. We could find L and take the roots. That's a bit too much work. Let's call this f. If we minimize f, we've minimized L squared. If we've minimized L squared, we've minimized L. We've discussed that before. Okay, so what's f prime going to be? So f prime, that's going to be 2x plus 1 plus 8. We can simplify this a bit and write this as x plus 1 over x, and then chain rule minus 1 over x squared. Okay, so you can treat that as a quotient, or you can simplify it like I did here. Either way, you're going to get the same thing. Okay, this is equal to 0. We can solve for x. We've got x plus 1 over here, another x plus 1 over here. X plus 1 is certainly non-zero, so we can get rid of that. And simplify, we end up with 1 minus 4 over x cubed is equal to 0. So the x plus 1s, we cancelled. We divide by 2, so that becomes 1, and then the 8 becomes 4. x squared and x, that gives us x cubed. Okay, so multiplying across, we get x cubed must be 4, so x is 4 to the third. So that is the distance away from the wall that will give us the minimum ladder length. Okay, very similar problem to what we covered before. You calculate the length, you differentiate the length, you solve for x. If the question then asks you what is the length of the ladder, you take this value x and you put it back and you get the length L. Okay, any questions? Okay, it's always the same method. Whatever the setup is, you convert it into equations, you find what needs to be minimized. So the question will say, find the shortest length, find the largest volume, find the least time. It always tells you what needs to be optimized. X, that will be your independent variable, whatever it is, depends on the situation. Differentiate, set to 0, solve for x. Always the same. Okay. Any questions? No. Okay. Please remember tutorials due Monday, no later than 12.